All right. So the next question is multiple hypothesis testing. So this really is relevant to the question. We have a high throughput experiment, and in the whole genome, there are about 20,000 genes, and we did this differential expression analysis. We tested the expression of every gene between one group of samples and another group of samples, and we are asking, is it different? And at the end, you can rank the genes by their level of differential expression, but where do you cut the line to say, between the two conditions, I have 200 genes that are different, or 500 genes that are different, or 1,000 genes that are different? Can we use p-value for something like this? Because basically, if you use the negative binomial distribution, or if you convert the original data into a log normal, you can also use t-distribution to calculate the differential expression. Each can give you a p-value, right? Can you use the p-value to give you to decide how many genes to cut?
No, like suppose you like a piece of 5%, you have a 10,000 genes, 500 of them will be significant because they are false.
Right. Yeah. That's definitely the right answer. So we mentioned here that when we try to test the differential expression for every gene with a p-value, supposedly on every gene, you decide you want to use 0.01 as cutoff. And if this gene is, if you decide this is not differentially expressed, that's the null hypothesis. If the genes are really differentially expressed, it's called the alternative hypothesis. You will reject the null and really cause something to be differentially expressed. If something meets the p-value cutoff, the situation as just the student mentioned, in the genome, we have 20,000 genes. If you use this 0.01 as cutoff, a p-value as cutoff, there are going to be 200 genes that are being that will be called, because you have so many genes. By chance, you will have 200 genes that have a p-value less than 0.01. And so even if you have no genes differentially expressed, you will still call about 200 genes, and probably all of them are wrong. This is similar to a situation like this. Today in the classroom, I'm trying to ask, how do students decide whether they are going to sit in the first half of the classroom or the second half of the classroom? I could try different things. I say, okay, let's first try undergraduates all sit in the front. No. How about people with glasses all sit in the front? No. And all male students sit in the front? No. People who live within the, or who are from the US will sit in the front, or who wear sweaters will sit in the front. Like if you try enough times, maybe we will see that, oh, all of those who have a sibling and ate noodles yesterday sit in the front, right? We just don't know. But if you would try 20,000 different things, maybe one of them will be a hit, right? Or some of those will be, will indeed be able to separate the students in the front versus the students in the back. But that's just because I've tried many different options. It's the same situation with looking at 20,000 genes and asking whether they are different. And so we need to make sure we control for multiple hypothesis testing. And one way to do this is to make sure that I don't wrongly call even a single gene incorrectly. And this is called the family-wise error rate. So this is the probability of rejecting at most one hypothesis at less than at a certain cutoff, which means the probability of not even calling one of them wrong is going to be 1 minus this number. So supposedly, if I want to correct for the family-wise error rate at 0.05 would mean that for whatever number of genes I call, even one of them is wrong, is lower than 0.5 probability, then I have to use on each individual gene a much more stringent p-value. Okay, so the way to do this, we wouldn't go to the statistical deduction is to use this Bonferroni correction to really control the family-wise error rate. If you have M hypotheses to test, and you want to control the final, whatever number of genes you call, I want not even a single gene to be wrongly called at this level of confidence, say 0.05 confidence, then for each individual gene, our p-value cutoff need to be alpha divided by this M, which means if they say in a RNA-seq experiment, if the alpha is 0.05 and we have 20,000 genes to make the prediction, the p-value cutoff would be 0.05 divided by 20,000, which is a very small number. And so sometimes when you don't have so many replicates, or the data is fairly noisy, you may not be able to see any genes to be differentially expressed, at least at this cutoff. And so this is too conservative in terms of multiple hypothesis testing correction. And so what have been used are this other concept called false discovery rate. And so if we look at the a study like this, so the rows are the truth, okay? The truth is H0 is your null hypothesis. You say the two conditions or the two groups of samples are actually similar. There's no difference in between the gene expression. In the alternative hypothesis, you are saying that actually the two genes are different. And then if you look at the columns here, that means this indicates for whatever statistical test, you are going to really make a call to say they are different, or make a call to say they are not different, which means whether you reject or not reject the null hypothesis. And so what is this U in this case? So U is this group, so for a particular gene, the two groups are quite similar, and you also did not call it as different. What is this? It's a true negative, right? This is a true negative, that's U. What is V? It's a false positive, right? Because these two groups are similar, but you call them as different. That's a false positive. T is a false negative, right? These two groups are different, but you didn't call it. That's a false negative. And then the S is a true positive, right? And so, yeah, as we mentioned, the false positives are what we call type 1 errors in statistics. And the T, which is the false negatives, are the type 2 errors. False discovery rate is the V divided by R. R is basically all the things we called. So we are trying to ask, out of all the calls we make, how many are false positives, or what percentage are false positives? That's the false discovery rate. Okay, so basically when you do a RNA-seq experiment, you want to see some genes are different. And even if there are some mistakes in occasional genes, you can tolerate that. Supposedly, if you say, I want to call whatever number of genes to be different, as long as the total wrong calls are no more than 2%, that's okay, right? If I call 200 genes and 2% is false, that's 40 genes, that's okay. So 160 genes are still correct. That's false, controlling false discovery rate at 2%, okay? And so you can see family-wise error rate is to make sure that out of those 200 genes, not even single one of them are wrong, or at this probability, whereas FDR just says out of the 200 genes or whatever number of genes you call, X percentage could be wrong. You don't necessarily know which ones are wrong. You just know roughly X percentage of them could be wrong. And so So the way to calculate this, I stole this from the StatQuest by Joshua Starmer. By the way, in the course schedule, you will see the lecture slides and the videos, and the bottom are other videos I found on YouTube. I would say sometimes, and probably most of the times, some of these other videos are really quite good, and you should watch those as well. I especially like this StatQuest by Joshua Starmer. And so I just did a screen dump from his YouTube video to show you. So this is also part of this homework one. You can see what we ask you to try this. You know, you use a random number generator from, say, uniform or some same distribution, and you just generate some group of samples to look at their difference. Let's just say, supposedly you have a random number generator to generate a differential, to generate numbers. Let's just make them simple. If the distribution that you generate this number is a normal distribution, and say you randomly generate 10 numbers in group 1 and randomly generate 10 numbers in group 2, and you calculate their differential expression using a t-test. That will give you a kind of you know, each will give you a normal distribution. And when you look at their difference, most of the time you will not see a significant p-value, but then occasionally you will see a small p-values. But if you look at all the different p-value distribution, it should be uniform. That's what p-value means, because it's the same distribution. You just randomly generate numbers, you test whether they are different. It should be a uniform distribution in here, right? So from 0 to 1, and every data has the same probability of hitting a particular p-value. And this is all noise. But if indeed there are some genes on this experiment that are different because of the treatment, it would mean that underlying there are two different distributions. Supposedly one is a normal, the other is a drug treatment, or one is normal, the other is a disease state. Then when you are randomly generating numbers from the first distribution versus the second distribution, and then test them and look at the p-value, you probably see something like this, right? The p-value is much more skewed towards a smaller p-value because indeed they are coming from different distributions, right? So the reality of the data we are getting is a mixture of the two, because you are dealing with 20,000 genes on this, in the genome, and most of the genes in the experimental condition. I think we can make some safe assumption that anytime you treat with a real cell, live cell, with a drug or something, most of the genes are going to be staying roughly the same. The genes that are changing is only a subset. And so most of the genes will give you this type of noise, uniform distribution, but only a subset of the genes, a tiny portion of those genes will give you a true signal that's skewed towards the left. But when you mix them together, this is what you get. If you take a look at a particular experiment, in fact, if you want to test, anytime you test a lot of hypotheses, you might want to draw the p-value distribution to see whether your statistical test is good. Because if you normalize your data well and you've done your statistical test well, you should see a p-value like this, okay? What happens if after you finish an experiment and you run the statistical test and then look at the p-value of all the genes in an RNA-seq experiment, you only see this? What does that mean? If you see something like this in the p-value distribution, it would mean that your data is too noisy. There is no differentially expressed genes that are significant from your experiment, okay? Whereas very often we see something like this. By the way, if there's no differentially expressed genes, the uniform distribution should be, the y-axis should be at 1, and it should be quite even to cover this area. But if there are real signals that some genes are truly differentially expressed, you have more area on the small side, and that's going to take the area away from the rest. And so this area may not really, sorry, these bars may not really reach 1. It might be 0.9 or 0.95 or whatever, right? So it's a slightly lower number than 1. Remember, we're saying that this is kind of a addition, like the sum between the noise and the signal. Therefore, if we say we want to do a p-value cutoff at this first bar, how much is the signal and how much is the noise? We would say actually any p-value, roughly, the noise will already give you this level of p-value below that bar, right? Just random chance, even if the two distribution have no difference. So these numbers or these genes are gonna be the random noise, whereas anything above this dotted line, these are the real signals. And so what is the FDR if you cut off at this level? So FDR is the false positives divided by all the things you call. It would mean that if you were to cut off if you are gonna call differential genes at this particular p-value, your false positive is, how many genes are you gonna call? If you're gonna call a p-value at this cutoff, you're gonna call everything to the left of this as differentially expressed, right? But out of all of these genes, anything below this dotted line, these are all random garbage from the noise. But everything above it, that's the real signal. So the FDR would be this little area divided by the whole bar. And so then if you were to cut at another p-value, let's cut off at here, it would be, the noise would be everything below this dotted line here, divided by all the genes that are called below this p-value, which include this bar together, right? So basically the intuition is that every particular p-value cutoff, you know that the A part is coming from random noise, and the B part is the real signal, and the false discovery rate is roughly A divided by A plus B. So A plus B is all the genes you're calling below that p-value. And you know that the noise in that, the potential false positives are estimated based on this lower dotted line, which is kind of, you estimate based on the right side. So that's why if you design a good statistical test, if you capture the correct distribution of your data and you do the right statistical test, after you finish testing all of your genes, that p-value should give you something so that the right side is pretty flat. And you can use that flat level, like extrapolate the flat level to the left to estimate roughly how much is your noise. And the remaining ones you called are the real signals. Okay, and so as we mentioned, in this situation, you just know roughly at each p-value cutoff, how many genes you're gonna call, and roughly out of those, how many are false positives. You don't know which one is the false positive. You just know a percentage of them are gonna be fake. Okay, that's FDR. There is a one-to-one correspondence. Basically, you can imagine at every p-value cutoff, you can estimate the A divided by the A plus B. Okay, and so the FDR value is always higher than the p-value. Because this is basically p-value is whatever cutoff you have. But below that, there are always something that are fake. Okay, and so FDR is basically a less conservative way to do multiple hypothesis correction than the family-wise error rate. There are a very widely used method called Benjamini-Hochberg method. It estimates this FDR. You know, the rough idea is like this. You estimate by extrapolation from the right side. You know all of the things on the right that give you the level of noise, and this will tell you how much truth you are going to have. You might see FDR. You might see, depending on the algorithm, they say adjusted p-value, and sometimes you might see Q value. They all mean the same thing. Adjusted p-value is the multiple hypothesis testing adjusted p-value. That's the same as FDR. Or Q-value is all the same. And as we mentioned, p-value and FDR are always monotonic. So every p-value has its corresponding FDR, and it's also bigger than the p-value for the same gene. So at the end of differential expression analysis, for each gene, based on the negative binomial distribution, you will get a p-value. And by looking at all of those p-values together, you will also estimate an FDR. And usually people take that FDR values. And so in order to really report genes, some people take 1% FDR, some people take 5%, some people take 10%. At least when you say I'm reporting FDR, the readers would understand that you have already done multiple hypothesis testing correction, right? And sometimes people, in addition to the FDR, they also filter by fold change. Say the fold change needs to be 1.2 or 1.5 or 2 fold change. But in general, with this FDR estimate, you can really get a sense of the signal to noise of all the hits you're calling. Most of the time, in reality, is people are comfortable with calling between, I would say, 50 genes and 3,000 genes as different. If after all of this, you get 3 genes that are different, you're kind of wondering, okay, maybe my experiment is too noisy, you know, something is wrong. But if you're calling too many genes as different, you might want to use more stringent, like if you see 5,000 genes as different, maybe you want to use a more stringent FDR cutoff, or you want to also add a filter for fold change, okay? One way to, so you can see basically the level of noise you have in the data versus the signal depending on, so supposedly if I have only 300 genes that are differentially expressed, but I'm doing 20,000 random other genes, the noise is 300 out of all the 20,000. But if instead of 20,000 genes, I only look at 5,000 genes, then the noise level would be much, much lower actually, and the signal would be much higher. And so is there a way we can reduce the multiple hypotheses we're testing? If you have a lot of noise, like if you have to test 10,000 genes, well, of course in human we don't have 10,000 genes, but suppose that you have 10,000 noise versus 300 signal, it's going to be a lot harder to call. But if you have only 5,000 genes and 300 signal, it's easier to call. But how do we reduce the number of hypotheses in this case? So algorithms such as DE-seq will try to ignore genes if it has too low gene expression level in too few samples. This gene is hopeless, right? What's the point of testing differential expression? You know you will never really actually reach a p-value significance. So with DE-seq, there are some simple heuristic to say, oh, if this gene is expressed, say you have 6 or say 10 samples, and you only see a single number in one of the sample, and the remaining samples are all 0. It's hopeless. This will never really reach p-value. And so DE-seq will use some simple heuristics to remove those genes that have too low expression level in too few number of samples to reduce the total number of genes to test. This way, the number of noise will be reduced and the signal will be higher. Okay, yeah, but at the end, most people are most comfortable with usually a few hundred differentially expressed genes. Questions about FDR? I would, yes.
Would you explain again why FDR is larger than p-value?
Because if you cut off at 5% p-value, and if there is no differentially expressed genes, do you know what your FDR is? It's 100%. All of them are fake, right? But if out of the, supposedly you do a cutoff and 50% are real and 50% are true, then you have 50% FDR, and that p-value you can see here. In each of these are all of your fake ones. And these are your correct ones, right? You are trying to estimate this % of fake with the total compared to all the others. the bottom ones give you that p-value, right? And so FDR is always bigger than the p-value. Okay. Yeah. So I would say the best thing statisticians have done to teach biologists is about multiple hypothesis testing. With high throughput sequencing, I would say before there is any high throughput experiment, people didn't really care as much about statistics. You know, biologists, they just feel like, oh, if I see different, anything different, I'll report it. I have a paper, that's great. Starting from gene expression microarrays, when people started looking at thousands of genes or tens of thousands of genes, they realized that you need to learn about multiple hypothesis testing. And I think that's really something statistics helped with biologists. And so basically, after a microarray experiment, you use DE-seq negative binomial distribution to call the differential gene, then use the FDR to estimate how many genes you really want to call, so that whatever number of genes you call, maybe only 5% of those are wrong, and the remaining ones are going to be correct. Okay?